Hess's law, standard enthalpies of formation, bond enthalpy, and lattice energy. Hess's law states when reactants are converted to products that the enthalpy change is the same, whether the reaction takes place in a single step or a series of steps. This is because enthalpy is a state function, meaning that only the final and initial states are important, not the path the reactions take. For example, the enthalpy of sublimation of water can be obtained from the enthalpies of fusion and vaporization for water. Water going from solid to liquid has an enthalpy of fusion of 6 kilojoules per mole. Water going from liquid to gas has an enthalpy of vaporization of 44 kilojoules per mole. Combining the two reactions and removing the liquid water from both reactant and product sides yields the chemical equation for the sublimation of water, that is, water going directly to gas from the solid state. The enthalpy of sublimation is the sum of the enthalpies of fusion and vaporization, which is 50 kilojoules per mole. Over the next few slides, I will be going over the use of Hess's law to calculate the standard enthalpy of formation for liquid carbon disulfide from carbon and sulfur as in equation 4. We are going to be given the enthalpy of formation of carbon dioxide from carbon and oxygen, equation 1, the enthalpy of formation of sulfur dioxide from sulfur and oxygen, equation 2, and the enthalpy of reaction for the combustion of carbon disulfide with oxygen to form carbon dioxide and sulfur dioxide, equation 3. The graphic here at the bottom is a picture of the carbon disulfide molecule. Rearrange the reactions such as the chemical species that are reactants are on the reactant side of their respective equations in the correct quantities, and that the chemical species that are products are on the product side of their respective equations in the correct quantities. Change the enthalpies to coincide with the changes made to the given reaction. If the reaction must be reversed, change the sign of the change in enthalpy. Exothermic reactions become endothermic reactions, and endothermic reactions become exothermic reactions. Second, if the reaction must be multiplied or divided to change the coefficients, then the enthalpy must also be multiplied or divided by that same amount. First, let's consider graphite, carbon, in the overall equation. If we look at the first equation, graphite plus oxygen makes carbon dioxide. Carbon is the reactant in the proper quantity such that the reaction and the energy will stay the same. Thus we have carbon as graphite plus oxygen makes carbon dioxide as a gas with the enthalpy of formation of negative 393.5 kilojoules. Second, in the overall reaction, we need two sulfurs. The chemical equation for sulfur reacting with oxygen has the sulfur as a reactant, except that the desired reaction has two sulfurs, and this second reaction only has one sulfur. Thus, we must multiply the reaction and the associated energy by 2. Thus, we have two sulfurs in the rhombohedral form react with two oxygen molecules in the gaseous form to form two sulfur dioxides in the gaseous form. The enthalpy of formation of the sulfur dioxide negative 296.1 kilojoules must be multiplied by 2, giving negative 592.2 kilojoules. The third aspect is putting carbon disulfide liquid as a product in the reaction. The chemical equation for carbon disulfide reacting with oxygen has the carbon disulfide as the reactant, and the resulting reaction has carbon disulfide as the product. We must reverse the reaction and change the enthalpy, giving a carbon dioxide reacting with 2 sulfur dioxide forms carbon disulfide liquid and 3 oxygen molecules. The enthalpy of this reaction is the negative of the heated reaction for the combustion of carbon disulfide, giving us positive 1072 kilojoules. To form the overall reaction, add up the reactions crossing out the chemical species that are common to both reactant and product sides, then add up the associated enthalpies. The total reaction before crossing out the common chemical species is carbon plus 2 sulfur plus 3 oxygen molecules plus carbon dioxide plus 2 sulfur dioxide makes carbon disulfide plus 3 oxygen molecules plus carbon dioxide plus 2 sulfur dioxides. Down here is the overall reaction. Removing the 3 oxygens plus the carbon dioxide and the 2 sulfur dioxides from the reactants and products yields the overall reaction of carbon plus 2 sulfurs makes carbon disulfide. Adding up the enthalpies for the 3 reaction parts, the enthalpy of formation of carbon dioxide, 2 enthalpies of formation of sulfur dioxide, and the negative of the enthalpy of combustion of carbon disulfide, gives an enthalpy for the reaction of 86.3 kilojoules. An arbitrary scale was established with the standard enthalpy of formation as a reference point for all enthalpy expressions. Delta HF 0 is the heat change that results when 1 mole of a compound is formed from its elements at 1 atmosphere. The standard enthalpy of formation of any element in its most stable form is assumed to be 0. For example, the enthalpy of formation of O2, which is the stable form of oxygen, pictured here, is 0, whereas a more unstable form of oxygen, ozone, O3, pictured here, has an enthalpy of formation of 142 kilojoules per mole. For another example, we have carbon as graphite. This is considered the more stable form of carbon, and its enthalpy of formation is 0. However, a diamond has a slightly higher enthalpy of formation at 1.9 kilojoules per mole. This table shows the standard enthalpy of formation for several compounds. There are several things to note about the enthalpies of formation. First, most of the enthalpies are negative, indicating that the compounds are more stable than the elements that they are formed from. Second, liquids have more negative enthalpies than the corresponding gaseous compound. See water for an example. As a gas, water has an enthalpy of negative 241.8 kilojoules per mole, while the liquid form has an enthalpy of negative 285.8 kilojoules per mole. Third, single atoms of the generally diatomic molecules have positive enthalpies, which we will find later are related to the bond enthalpy of the diatomic molecule. For example, it takes 218.2 kilojoules per mole to create a single hydrogen atom from the more stable diatomic form, and it takes 249.4 kilojoules per mole to form a single oxygen atom from diatomic oxygen. The standard enthalpy of a reaction is the enthalpy of that reaction when carried out at a constant pressure of 1 atmosphere. As a result, the standard enthalpy for the reaction is the final state, which are the products, minus the initial state, which are the reactants. This first term is the sum of the enthalpy of formation of each of the individual products times their stoichiometric coefficient. As shown below in this reaction, the products are C and D, so the sum of the enthalpy of the products would be the stoichiometric coefficient C times the heat of formation of C plus the stoichiometric coefficient of D times the heat of formation of D. The second part of the equation, we're taking the sum of the enthalpies of formation of the reactants, multiplying those by their stoichiometric coefficients. In this general reaction below, we have the standard enthalpy of formation of A times its coefficient A, and the standard enthalpy of formation of B times its coefficient B. Using the combustion reaction of carbon disulfide with oxygen to produce carbon dioxide and sulfur dioxide, the enthalpy of the reaction is the enthalpy of carbon dioxide times 1, because there's only one carbon dioxide as a product, plus the enthalpy of formation of sulfur dioxide times 2, which is the coefficient for sulfur dioxide, minus the enthalpy of formation of carbon disulfide, which is a reactant. And note here that the enthalpy of formation for oxygen is not given because the oxygen has an enthalpy of formation of 0, as defined previously. Calcium carbonate decomposes into calcium oxide and carbon dioxide upon heating. What is the enthalpy of this decomposition? Here we have calcium carbonate becoming calcium oxide and carbon dioxide. The enthalpy of formation for each of these components is given here. To find the enthalpy for the reaction, we're going to take the enthalpy of formation of calcium oxide, which is negative 635.6 kilojoules per mole, and multiply that by 1. We're then going to take the enthalpy of formation of carbon dioxide, which is 393.5 kilojoules per mole, and multiply that by 1. And then we're going to subtract from that the enthalpy of formation of the product, of the reactant, calcium carbonate, which is negative 1206.9 kilojoules per mole. So we're subtracting that, giving a net result of 177.8 kilojoules per mole. Benzene, C6H6, burns in air to produce carbon dioxide and liquid water. How much heat is released per mole of benzene combusted? The standard enthalpy for benzene is 49.04 kilojoules per mole. The reaction is 2 benzene molecules plus 15 oxygens form 12 carbon dioxides and 6 waters. The standard enthalpy of the reaction is thus 12 times the standard enthalpy of carbon dioxide, which is negative 393.5 kilojoules per mole, plus 6 times the standard enthalpy of formation for liquid water, which is negative 285.8 kilojoules per mole, minus 2 times the standard enthalpy of formation of benzene, which is 49.04 kilojoules, resulting in an overall heat of reaction of negative 6,534.9 kilojoules. To get the standard enthalpy for the reaction per mole of benzene, the final enthalpy must be divided by 2 because there are 2 moles of benzene in the overall reaction, which gives negative 3267.4 kilojoules per mole of benzene. An alternative approach would be to divide the entire reaction by 2, such that you start with only 1 benzene. The resulting calculation would have half the amounts of carbon dioxide, water, and benzene. So the overall reaction when divided by 2 would be C6H6 plus 15 halves of O2 makes 6 carbon dioxide plus 3 water. And then we would do the calculation as normal, but it already comes out in per mole of benzene. Bond enthalpy is the enthalpy change required to break a particular bond in 1 mole of gaseous molecules. Bond strength increases with bond order. That is, single bonds are generally weaker than double bonds, and double bonds are generally weaker than triple bonds. Here are 3 examples of single bonds. Separating hydrogen into 2 individual atoms takes 436.4 kilojoules per mole. Separating the single bond in the chlorine molecule to make 2 chlorine atoms takes 242.7 kilojoules per mole. The difference between these two has to do with the size of the atoms in the molecule. The bond distance in the hydrogen molecule is smaller than the bond distance in the chlorine molecule, making it harder to break. The single bond in HCl has an energy of 431.9 kilojoules per mole. Now let's look at a double bond. The double bond in oxygen takes 498.7 kilojoules to divide it up into 2 oxygen atoms. And here's a triple bond. In nitrogen, it takes 941.4 kilojoules to divide the nitrogen molecule into 2 nitrogen atoms. Lattice energy is the energy input required to completely separate 1 mole of a solid ionic compound into gaseous ions. Formulaically, the lattice energy is directly proportional to the charge on the cation, Q+, times the charge on the anion, Q-, and is inversely proportional to the radius between the 2 charges, R. The result is that the lattice energy increases as the magnitude of the charges increase, or as the radius decreases. Conversely, the lattice energy decreases as the charges decrease, or as r, the radius, increases. We will not be doing any calculations with lattice energy, but we will analyze the effect of increasing the charge or changing the radius in the next slide. Another thing to note that lattice energies are generally higher than bond enthalpies because lattice energies deal with electrostatic forces, which are much stronger than bond enthalpies. This table shows a comparison of 3 different pairs of ionic compounds with their conditions and lattice energies. Comparing magnesium fluoride with magnesium oxide, the charge on the cation remains the same at +2, but the charge on the anion doubles from -1 to -2. As shown, the lattice energy increases from 2,957 kilojoules per mole to 3,938 kilojoules per mole. As it states in note 1, the lattice energy does not simply double because the radius also increases as fluoride is exchanged for oxygen. So the overall result is one of the charges increases. As a result, the lattice energy increases. Second, we're going to compare the effect of radius by comparing lithium fluoride with lithium chloride. The charges do not change at all, but the radius of the fluoride is less than the radius of the chloride. This increase of radius from fluoride to chloride results in a decrease in lattice energy. Increasing radius, decreasing lattice energy. Goes from 1,036 kilojoules per mole down to 853 kilojoules per mole. Lastly, if we compare lithium fluoride and magnesium oxide, which is done to show the effect of changing the magnitude of the charges without substantially changing the radius between the ions. Lithium fluoride has a radius of 209 picometers, while magnesium oxide has a similar radius, being only 212 picometers. The magnitude of the charges increases from +1 and -1 in lithium fluoride to +2 and -2 in magnesium oxide. Multiplied together, this is a 4-fold increase in the numerator of the lattice energy, and it can be seen that the lattice energy nearly quadruples from 1,036 kilojoules per mole in lithium fluoride, which is +1 -1, to 3,938 kilojoules, which is +2 -2 in the magnesium oxide.